Distillation is a very important concept to understand in chemical engineering. In industry, distillation is a widely used technique by chemical engineers to perform separations of systems involving, or fluid streams involving things like water and alcohol or crude oil. And if you've ever wondered how do beverage companies like AB Bev extract alcohol and concentrate it into the form that you can buy a beer in, or vodka if that's your preference. The trick is to perform distillation. And in the oil industry, the question is, how do you extract different grades of fuel from crude oil? Again, chemical engineers will be called upon to perform distillation to extract the desired grades of fuel. And the premise of distillation rests on a difference in boiling points between two substances. And as an introduction to distillation, we typically stick to binary systems, meaning two components. So we'll have component A and component B, and we will focus primarily on how do you model and derive how many stages and what kind of quantities you can expect to work with based on the more volatile component, which again we typically label as A. And so a simplified schematic of what a distillation column here is shown. And what we have is a feed stream labeled F with a composition ZF, so molar ratio, and a quality called Q. I'll get to what quality refers to later. These capital letters, capital F, capital D, and capital B, refer to total molar flow rates, and the lowercase letters ZF, XD, and XB refer to the molar ratios. And so what happens in a distillation column is we'll have a feed stream come in and enter, and depending on the quality of the stream, the feed will either be all liquid or all vapor or a mixture of the two, and it will either travel up or down the column. So we can think of this whole thing as a big tall column. So if you ever drive past on the freeway and see some industrial looking chemical separators, you'll likely see some distillation columns, and these things can get very tall, tens of meters high, and so they are very big. And the way they work is each one of these plates is operating at a different temperature. So as we travel down the column, it gets hotter. And so we have streams, we have within the distillation column a vapor stream that is rising based on its buoyancy, and a liquid stream that is flowing down the distillation column. And within the distillation column, we label our streams L and V, capital L and capital V, to denote the total molar flow rates of the liquid and vapor phases in the top half of the distillation column, or the segment of the distillation column that is above your feed plate. And then we denote the total molar flow rates beneath the feed plate as L bar and V bar, respectively. And within the distillation column, what happens at the very bottom is we enter something called a reboiler. And within the reboiler, we add heat into our system. We have some kind of Bunsen burner, some huge industrial heater, and we have a liquid phase entering, a liquid stream entering the reboiler. It gets heated up, and that stream, so two streams will exit from it, a stream called the bottom stream, which we call B, with a particular molar ratio of our more volatile component, which we call XB. And then the other part, the vapor phase, some of the vapor phase that's created in your reboiler, will get sent back up your distillation column. And at the very top of the distillation column, we have something called a condenser. And within the condenser, we extract heat. We're taking heat out of the system, and consequently, the incoming vapor phase cools down and becomes a liquid phase. And we take our liquid phase, and through a splitter, we convert it into a D stream, the distillate stream, with a molar ratio XD, the molar ratio of your component of interest, as well as we divert another part of it back down the distillation column. And it is important to remember that when we have two streams exiting a splitter, they both must have identical concentrations. So XD will be the same in both of these streams, as well as the inlet stream of our splitter. And an important term to define right now is something called the reflux ratio, R, and that is the ratio of L over D. So that is how much, it essentially tells you how much of the distillate are you extracting and how much are you diverting back into your column from the exiting stream of your condenser. So if you have no reflux ratio, that means you are taking the maximum amount of distillate as you can out of the system, and consequently R would equal 0. And so that would be the case if you wanted to maximize the molar flow rate of D. The reason you would want to have or run a higher reflux ratio is if you wanted to have a higher purity of XD. So if you wanted to concentrate your component of interest more, such as alcohol or ethanol, we would turn to higher reflux ratios, which we'll get to later on. And the way we define quality is assuming we're not dealing with subcooled or superheated streams of fluids, meaning we're not cooling them below their melting point or raising them above their boiling point, we can think of our quality term as the liquid fraction of the feed. So if your feed coming in is entirely liquid, that means, and it's at or below, so it's within a range, but it's at or below its bubble point. So bubble point's the boiling point essentially of your mixture. We can say that our quality is equal to 1. So the entire liquid, the entire feed is all liquid, and it will travel down and join up with the already downflowing liquid stream within your column. Now, if the feed stream is entirely vapor, in that case, it will be equal to 0. And this means up to this. So the dew point temperature is the temperature at which the vapor phase will begin condensing into a liquid, but not yet. So it's right at the limit. So as long as we assume that the incoming stream is all vapor at its dew point, we can use this assumption and call it 0. Q can take on values greater than 1 and less than 0, and that is the case when we're dealing with subcooled or superheated streams. But typically, as an introduction, we can gloss over that. And so the next point, after you've understood the core concepts of a distillation column, is to ask yourself, where do you put a feed plate? How many stages are you going to need? So each one of these is a stage. And what will be the composition in each one of these streams? And to do that, we turn to something called a McCabe Thiele diagram. And the McCabe Thiele diagrams are very useful diagrams we use that contain lots of information. And if you can understand how to use them, they are quite useful. The first thing to note about McCabe Thiele diagrams is that they are only used with binary systems. And when you are generating McCabe Thiele diagrams, it is common practice to follow graphing only the compositions of your more volatile component. The more volatile component is the one that has the lower boiling point of the two components in your inlet stream. So if we were dealing with a water and ethanol inlet stream, ethanol would be what we would generate our McCabe Thiele diagram based on, and ignore water because its boiling point is lower. The next step we do when making a McCabe Thiele diagram is to create diagonals and plot an equilibrium curve. And in my chemical engineering classes, what we do is we use MATLAB to create these plots and derive the lines. And you can quite easily do this by defining different lines and calling the plot function with x1, y1, x2, y2, x3, dot, dot, dot. And so analyzing a McCabe Thiele diagram before we've generated it, just so we know what we're going to be looking at, we have, I'm going to label this one actually line 4. Line 1, so on a test you'll typically be just given a McCabe Thiele diagram and then told to answer questions about how many stages you'll need and stuff like that. The line that we see right here, actually I should probably start by saying what some of these points are. So within the McCabe Thiele diagram, we can start off with by looking at the points of intersection between the diagonal and our composition, our molar ratios in our distillate, feed, and bottoms streams. And so the first point that we can look at on our graph is the XD ratio. And so XD is the desired purity. So if I wanted to create a stream of ethanol that had 65% purity in its distillate, that means that XD would equal 0.65. So I would plot the line 0.65, 0.65 on a 2D plot, and with an equilibrium curve, we can derive relationships. But the line that we derive from this XD point is called our rectifying line. And the rectifying line is derived from a mole balance on the top half of the distillation column. The next line that we care about on McCabe Thiele plots is something called the stripping line. And the stripping line has a point XB. So XB is the molar composition of your bottoms stream, and the slope of that is something we'll get to. And the Q line is a line generated on your plot based on the ZF point intersection with the diagonal, and Q, so the quality of your feed. So changing Q will change the slope of this line, and we'll get to that. And finally, we have an equilibrium line that we derive using Rayold's law. And so on a homework or on a test, unless you have access to MATLAB, it's pretty hard to generate accurate equilibrium lines. But when you do have access to a computer, what you will have, what we use to generate our equilibrium line is Rayold's law. Rayold's law tells us that Y sub I, the molar ratio of some component I in the vapor phase times the total pressure, must be equal to X sub I, the molar ratio in the liquid phase, times Pi sat. And if we recall what the definition of K, the equilibrium constant, is, K tells us what the ratio of the molar ratios are between the vapor and liquid phase respectively. So K sub I is equal to Y sub I over X sub I. And this version of Rayold's law is assuming that we are working with ideal gases and ideal liquids. If we had non-ideal liquids, we could take that into account by inputting an activity coefficient here, but for the sake of simplicity, we'll ignore that for now. And so we can define K sub I values given a particular temperature based on the saturation pressures. And so to find out what saturation pressures are, we look at something called Antoine's equation, which is something taught in thermodynamics courses. Antoine's equation tells us how the saturation pressure of a particular substance will change as a function of temperature. And other parameters, typically they're denoted A, B, and C. And so what we would ultimately find, based on our Antoine's equation, is the pi sat of the two components in your binary system at a given temperature. The next step to deriving an equilibrium curve is to define another variable called alpha. And alpha is the relative volatility of your two components. We call it K1 over K2. In the case where it's an ideal liquid and ideal gas, we can simplify this to P1 sat over P2 sat. And once we know alpha, alpha is consequently also a function of temperature, because P1 sat and P2 sat are also functions of temperature. We can further define the equilibrium curve to be y is equal to alpha times x. So the molar ratio in the vapor phase is equal to the relative volatility times the molar ratio in the liquid phase, divided by the quantity 1 plus x times alpha minus 1. And this will give us a point on our curve. So within MATLAB, you'll declare a vector x ranging from 0 to 1, and you will calculate y sub I at particular x values within your vector. So you'll have two n by 1 vectors to plot simultaneously onto a 2D plot, which will give you an equilibrium curve. Your equilibrium curve, if you follow the steps correctly and are only looking at your more volatile component, should bow upwards. So if it's bowing downwards, you've done something wrong and you'll need to possibly change which component you're analyzing. And so after you've found your equilibrium curve and you've plotted your diagonal, the next step is to plot either. So two lines intersect at a point, which we learned in geometry. We only need to graph two of these first three lines that I defined to obtain an intersection to derive the third line. So in this case, if we were given enough information in the problem statement to define a rectifying line, the rectifying line is this top line here labeled 1. What we can do is look at the slope. So if we know our reflux ratio, which we define above to be L over D, and we know a point on that line, we know that the slope, based on our derived mole balance, which you can go into a textbook or a lecture and view, must be equal to R over R plus 1. And note how this will be this should have a positive, this will have a positive quantity, or you can also define it as L over V, the ratio of the liquid flowing down your distillation column relative to the ratio of the molar flow of the vapor rising up the column. And so intuitively we can ask ourselves, what happens if I increase the liquid flow rate substantially? How is this graph going to change? So if you increase your liquid flow rate while holding your vapor flow rate constant, the slope of this line will increase. Excuse me. So because the slope is increasing, we would expect it to collapse down a little bit, and it changes the number of stages that we will need consequently, which we can analyze. We will analyze in about a minute. And the next line we can define is something called the stripping line, and the slope of that line is the boil-up ratio plus 1 divided by the boil-up ratio. The boil-up ratio is a term that we define to be how much of the vapor we return into our distillation column relative to the amount, the flow of the bottom stream that we extract from our reboiler. And the slope of this line, so that tells you what VB is. The slope of this line is also equal to, and you can prove this algebraically, L bar over V bar. So the ratio of these streams on the bottom half of the distillation column. The final line we can define is the Q line, which is based on the quality of your feed. The slope of that is equal to Q over Q minus 1. And once you have defined all three of these lines, as soon as you define two lines, you can find the third quite easily. You can tell someone the boil-up ratio if you didn't know that. You could tell them the quality if you didn't know that, or you could tell them the reflux ratio given the other two. And what we can do at this point is, if I wanted a particular purity in the distillate stream, I can tell you how many stages will be needed to get to that desired purity. And so what we do is we start at this point, and this is our operating line for our rectifying section. The rectifying section is the top half of the distillation column. As we go across, we are reaching equilibrium. We hit our equilibrium curve. We are assuming that you hit equilibrium, or you reach equilibrium at a tray. So that means we will need one tray right here. We now return back down to our operating line and then go to equilibrium again. So every time we hit equilibrium, that means we need to have an additional tray. And so a second tray will be needed, and we can work our way down the distillation column until we reach a point that is beneath our bottoms composition of your more volatile component. And this gives you an idea of how many trays you will need in a real world. An interesting question to ask is, if we only made it 50% to equilibrium at each tray, how do we change this graphical analysis? So if we only make it 50% to equilibrium, that means that right here, halfway between our operating line and equilibrium, we stop. And in that case, I'll use a pencil, we only get to here. And what you will find is, regardless of, you will end up needing more stages as a result. So at this point here, we only made it halfway to equilibrium before we return to our operating line. Again, we make it about, so if we draw out what halfway would look like, it would be about there. So each one of these vertices is another equilibrium, is another tray you will need in your distillation column, and we can work our way down the plot. And what we end up finding is you're going to need 4 or 5 trays instead of 3 when you're not reaching equilibrium, which is taking into account a non-ideality of your system. And it all is dependent on your two components and the temperature and other variables. So this is something I would recommend one would have some kind of physical model to analyze and then use dimensional analysis and the Buckingham Pi theory before drawing any conclusions or submitting any applications to your supervisor. So that's what would happen if we did not reach equilibrium. And finally, last thing I'll say is if we wanted to know what the minimum number of trays we would need, if we wanted to know what our minimum value is for when we let So if I wanted to tell you what the minimum value of L over V is, the minimum flow rate of your distillation column is, I can do that via another graphical analysis by letting the rectifying line and the stripping line intersect the equilibrium line at a vertex here. And this tells me the slope of this line that I have written right here tells me what L over V minimum is. So I don't have much room to work here, but is equal to the slope. And by analogy, this slope here will also tell me what L bar over V bar minimum is as well. So with this, I can tell you what the minimum flow rate is within your distillation column. The problem is when you have, we refer to these as pinch points. When we have pinch points in our McCabe Thiele diagram, it causes problems because you need an infinite number of trays. And the reason for that is if we tried to see what would happen, everything looks good up to here, but then we reach a problem in here where you have infinitely many steps leading into your pinch point. So you never really do operate at L over V minimum. Typically you'll operate at 1.5 times L over V minimum, which usually gives you slopes that are a lot more realistic to work with, and number of trays that are what you would expect in practice to work with. So I hope you guys find this useful. Let me know if you have any questions, and thank you for watching.